Okay, then what if we have infinite domain? So, for instance, if domain is real numbers, then real numbers are uncountably many. There are a lot of possible input values. And if we consider hypothesis set as whole function, whole possible function defined on real line, then the hypothesis set also has infinitely many different functions. Okay. Then from the no free range theorem, what we can say is the pen running is impossible with the hypothesis set and with the input domain. Essentially, when we have infinitely many input element, and when we consider the whole possible function as the hypothesis set, to guarantee pen running epsilon test error, the required number of training samples should also be infinite. So the question is it impossible to learn something when we have an infinite domain set? The answer is yes, we can learn. So although the input domain is infinite, and even the hypothesis set we are considering also has infinite different functions, still we can learn something. For instance, neural networks. Neural networks, basically, the input values can be infinitely many. For instance, image classification task, we can receive infinitely many different image input. There's no restriction. And the function we can generate from a neural network also infinitely many. When we change one parameter of neural network, the neural network is a different function. So we can define infinitely many different functions from one single neural network because we have real number parameters, which means we can define infinitely many different functions. So we have very complicated hypothesis set and very wide range of input domain, but still we can train very well, and so success of deep learning, right? Okay, then how can we learn although such huge complexity? This is why we have to study VC dimension. Okay, the VC dimension tell us some complexity of algorithm, not by the cardinality, but from the smoothness or the shape of hypothesis class. For instance, our function class is linear function. Then the function, our hypothesis class consists of linear function. Then the hypothesis set is very simple. Okay. When we consider like a million degree polynomial, then the hypothesis set consider very flexible functions. In other words, we use very complicated hypothesis class which require a lot more training samples compared to the linear regression model, linear function model. But at the beginning of this week, I explained there exists bias and variance trade-off, or overfitting and underfitting issue, and approximation and estimation error issue. What does that mean is essentially when we consider very simple hypothesis class, we can expect good test error when the true function that really generates the output variable y belongs to the hypothesis class we are considering. Okay, so that is estimation error. The estimation error basically comes from the complexity of your hypothesis set. As you consider simpler form of hypothesis class, the estimation error becomes less because we restrict the function shape from few number of training instances. We can easily find some good performance in our hypothesis set. Okay, we can make a training process as very similar training error and test error. But when we use very simple hypothesis set, there are always risks such that our hypothesis does not include the true function, and even in some case the best function in our hypothesis has huge test error. This is called approximation error or bias error. So there is approximation error and estimation error, and there are always trade-off between approximation error and estimation